Question A. Find the first four terms in the binomial expansion over square root of 1 plus 5x in ascending powers of x. To find the required expansion, I will use the next formula, that 1 plus x to the power of n, where n is rational, is equal to 1 plus nx plus n times n minus 1 times x squared over 2 factorial, which is 2 plus n times n minus 1 times n minus 2 times x cubed over 3 factorial, which is 6, and plus so on. And this expansion is valid only when the absolute value of x is less than 1. Notice that it's not just x. When it's 1 plus 10x, you should consider the absolute value of 10x is less than 1. And to apply this formula, you should rewrite a given expression as 1 plus something to some power and apply this formula. So, square root of 1 plus 5x is 1 plus 5x to the power of a half, and it is equal to 1 plus nx plus n times n minus 1 times x squared. It's 5x and squared, so it's 25x squared over 2 factorial, which is 2 plus n times n minus 1 times n minus 2 times x cubed. Not just x, it's 5x as just x in this formula, so it's 5x and then cubed, so it's 125x cubed over 3 factorial, which is 6, and plus so on. And it is equal to, let's simplify, 1 plus 5 over 2x minus 25 over 8x squared and plus 125 over 16x cubed and plus so on. Question B. Find the expansion of 1 plus px multiplied by 1 plus qx to negative 1 in ascending powers of x up to and including the term in x squared. So 1 plus px multiplied by, and we apply the same formula. So it becomes 1 plus nx, so negative 1 multiplied by qx, so it's minus qx, plus negative 1 times negative 2n times n minus 1 times x squared, so qx squared, q squared x squared over 2 factorial, which is 2. And you can see it's plus 2 and 2, so 2 cancels, so it's just plus q squared x squared and plus so on. Let's expand, and we need up to and including the term in x squared, so 1 multiplied by 1 is 1, pq, 1 multiplied by negative qx, it's minus qx, 1 multiplied by q squared x squared is plus q squared x squared, then px multiplied by 1 is plus px, and px multiplied by negative qx, it's minus pqx squared, and x multiplied by x squared, it's cubed, which is not required, and plus higher powers of x, which are not required. Let's simplify, so it becomes 1 plus p minus q x plus q squared minus pq x squared and plus so on. The expansions found in parts A and B are identical up to the first 3 terms for value of p and the value of q. Question C shows that q is 5 over 4. So this is identical to this. And definitely we can equate coefficients in front the same powers of x. So we can conclude that p minus q is 5 over 2, and this, and we can factor out q times q minus p is negative 25 over 8, and q minus p, it's negative 5 over 2 is negative 25 over 8, and q is 5 over 4 as required. The next, the expression given with p and q can be used as approximation for this. So this approximately equals to this. And here you can see that the absolute value of this is less than 1, so the absolute value of x is less than 1 over 5. Hence, by finding the suitable value for x, find the approximation for square root of 1.2 in the form m over n, where m and n are integers. So 1 plus 5x should be equal to 1.2 to use. In general, the expansion for this as approximation of square root of 1.2, and in general you can use this expansion to find the approximate value of square root of 1.2, but here it is given that this is approximately equal to this, so we can use just this expression, but it is given that they are identical up to 3 terms, and if you substitute the found value for x into this, it will be the same, but it will be much easier just use this, because it is given that this expression can be used as approximation for this. So 5x is 1.2 minus 1 is 0.2, and 0.2 is 2 over 10 or 1 over 5, hence x is 1 over 25. And substituting the values for p, q and x into this, we can say that square root of 1.2 approximately equals to this fraction 1 plus p 15 over 4 x and 1 plus q 5 over 4 x. Let multiply each term in the numerator and denominator by 100 to get 115 divided by 105. We can divide by 5 to get 23 over 21, and it's in the required form. Then, now consider the approximation for square root of 5 over 2. Explain why the approximation for square root of 5 over 2 is not as accurate as the approximation for square root of 1.2. And again, to use this, we need the x value, this to be equal to this, so root of 5 over 2, it's a root of 5 over 4, and it is equal to root of 1 plus 5x. So 5 over 4 is 1 plus 5x, and it's 4 over 4, so it's 1 over 4 is 5x, x is 1 over 20. And notice that 1 over 25 and 1 over 20 are in between negative 1 over 5 and 1 over 5, so this expansion or approximation is valid at all, because if x is greater than 1 over 5 or less than negative 1 over 5, this approximation is not valid at all. And I repeat, in general, if you need the approximate value of something, first of all, you should check that it's true, this expansion is valid, and in general, we just use this and substitute the corresponding value for x and just calculate. And it's a specific question. It is additionally given that it is approximately equal to this, so we can use this. But here, for this question, it's not required to calculate the approximate value. We need to explain why the approximation for a root of 5 over 2 is not as accurate as the approximation for square root of 1.2. So for 1.2, x is 1 over 25, and for this, x is 1 over 20. And this expansion is actually the Maclaurin series, and it's the expansion about 0. And the closer x value, the closer to 0 x value is, the more accurate the approximate value is, the calculated value is. So we can say that as 1 over 20 is greater than 1 over 25, therefore approximation for root of 5 over 2 is not as accurate as the approximation for square root of 1.2. And that's all for this question.